So this is the example that I made up that I'm adding into our notes so that we can see an example with a whole. So we're going to start off by doing what we always do. We're going to completely factor the numerator and the denominator. The numerator factors into 3x minus 1 times x plus 4. There's a few ways that you could do that. You could use the quadratic formula on this piece right here. If you did the quadratic formula, you would get that x is equal to 1/3 and -4. And from those two x values, you should then be able to write these factors. Now let's factor the denominator. Denominator, notice it is of the third degree. So to factor that, you would want to use lesson 17 and use the rational zeros test, where you go and you test for zeros. And if you do that, you would find that this polynomial has zeros of 1/3, -1, and -5. So that means that 3x minus 1 is a factor because 1/3 is a 0, x plus 1 is a factor because -1 is a 0, and x plus 5 is a factor. So now that we have this completely factored, we're going to move on to step 2, where we look for wholes and vertical asymptotes. So first we check to see if anything cancels, and the 3x minus 1 does cancel. So first let me take a second to write this function now in simple terms. So I have the function written in simple terms. We've talked about how we definitely do have a whole because the 3x minus 1 is going to cancel out. To find the whole, you take whatever canceled out, the factor that canceled out, and you set it equal to 0. If I solve this by adding 1 and dividing by 3, we get that x is equal to 1/3. That is the x coordinate for where the whole is at in the graph. To get the y coordinate for that point, we have to plug 1/3 into simple terms. So when we plug 1/3 into simple terms, I get about 0.6 out. I'm just rounding that. So our whole is about at 1/3, 0.6. That's about the point 0.33, 0.6. That's just to help us graph it. So that is very, very, very close to the origin, especially on this scale. And I did just plot like an open point right there because it is literally graphed as a whole in the graph. So we have our whole. Let's go on to find our vertical asymptote, or vertical asymptotes, which we will find by grabbing the denominator from simple terms, and we will take that denominator and we will set it equal to 0. We then set both of these factors equal to 0 to get the equations of both of these lines for our vertical asymptotes. And again, these are the equations of lines. I already have them graphed. X is equal to -5 and x is equal to negative. Moving on to our third step, we're now going to be looking for our horizontal asymptote or our slant asymptote. It can have one or the other. Which one it has depends entirely on the degree of the numerator and the degree of the denominator. Here we can see that the degree of the denominator is larger. Every time the degree of the denominator is larger, it means that your function has a horizontal asymptote of y is equal to 0. If it has a horizontal asymptote, then it does not have a slant asymptote. The line y equal to 0 is actually the x-axis. So I'm just going to use a different color to try to stick that on there. But what that means is that as we draw the graph, we will see the graph level out along the x-axis, both as x gets really big and the graph goes off to the right, and as x gets really small and the graph goes off to the left. Now we're ready to go in and look for intercepts that this graph has. I'll start with the easiest one, finding the y-intercept. We find the y-intercept by setting x equal to 0, so I'm going to plug 0 into this function, and I get out a positive 4/5, because both the 4 and the 5 are negative originally, so it comes out to be positive. Just to help us graph that, that is the point 0, 0.8. So I'll go ahead and plot that on my graph. All of these points are very, very, very close to the origin, so we might not exactly see them, but we do have the work on our paper to show where we are getting them from. So we have the y-intercept. Now let's go on to find the x-intercepts. To find the x-intercept, we need to set the numerator of the rational function equal to 0. But we have to be careful because the question then comes up, which numerator should we use? Should we use this numerator or should we use this numerator? Well, we don't want to use the 3x minus 1 because remember, at that 3x minus 1 where we get 1/3, we have a whole happening there at that 1/3. So we do not want to use that piece. We're just instead going to use the x plus 4 numerator to use that piece to find our x-intercepts. So I'm going to be setting x plus 4 equal to 0. I get that x is equal to -4, so we have an x-intercept at the point -4, 0, which does happen to fall on our horizontal asymptote, and that's perfectly okay. That does happen sometimes, but we need to make sure that our graph definitely does not touch our vertical asymptotes. So now we are ready to look at the graph and find some extra points that are on that graph. We can use our calculator and our table to do that, to help us finish graphing this. So when I actually look at the graph, this is what I see. We can see our two vertical asymptotes right there. We can see the intercept that we found at -4, 0. We can see the y-intercept that we found there. Our graph is on a little bit of a different scale, so I'm just going to trace in something that is very similar to this. And remember, as we talked about in class, nothing stops you from looking at the graph first and then making sure that the answers that you're getting are matching up with the graph that you see. In terms of extra points, the extra points that you would have used down here for number 5, you would have made sure that you picked at least some other point that was on the piece all the way to the left. So for example, you could have chose 2 as an x value and just make a note of what y value you got out. You would have chose at least one other point on the piece in the middle. So for example, you could have chose -2 as that x value, and then you would have chosen 2 points on the piece all the way out to the left. So maybe -6 as an x coordinate and -8 as an x coordinate. The last problem we have in this lesson is an application of rational functions. Here we have a formula for calculating a child's dosage in medicine if we know the adult dosage. So this D is some number constant there that would be plugged into that function. X represents the child's age. So there's what all 3 components of this function are. And now let's go look at these questions. Part A is asking us for the horizontal asymptote of the function. So to find the horizontal asymptote, we need to be thinking about the degree of the numerator and the degree of the denominator. So our rational function, I've rewritten it here. The degree of the numerator is 1. And the degree of the denominator is also 1. So the numerator and the denominator have the same degree, which means that the horizontal asymptote is y is equal to the ratio of the leading coefficients. The ratio of the leading coefficient in the numerator is D, and the leading coefficient in the denominator is 1. So the horizontal asymptote is simply the line y is equal. Now think back to when we graph horizontal asymptotes. We graph the horizontal line, even looking at, backing at this example in number 3. We graphed this horizontal line at y is equal to 2. And what that meant was that when we drew the graph, we made sure to level out at 2. We said that's what's happening as x gets really, really, really big. It's talking about the end behavior of that function. We've written things like this before to talk about end behavior as saying as x gets really big, the y value goes to 2. The function tends towards 2. So let's think about what our horizontal asymptote means in the context of this problem. As x gets really big, y goes towards D. That's what this horizontal asymptote means. But if x is getting really big, x is the child's age. So in the context of this problem, it means as the child gets older, y is going towards d. The function goes towards d. Well, the function is the child's dosage. So instead of saying the function goes towards, I'll say the child's dosage goes towards, and it's going towards D, and D is the adult's dosage. So as the child gets older, the dosage that that child would take gets closer and closer to the dosage that the adult would take. And that makes sense because as you grow up, you no longer take the same smaller amount of medicine that you did when you were a child. You now take more medicine because you are bigger. Part B is asking us for the vertical asymptote of this function. This function is already written in simple terms. There's nothing that can cancel out. So to find the vertical asymptote, I'm simply going to take the denominator of x plus 12 and set it equal to 0 and get that the vertical asymptote is the line x is equal to negative 12. Part C is asking us to answer a question. It says for an adult dosage of 50 milligrams, 50 milligrams is our value of D because that is the adult dosage. What is the approximate dosage for a 9-year-old child? A 9-year-old child, that gives us our X value because X is the child's age. So we want to evaluate C of 9. We want to plug 9 into the function. So instead of writing dx, I'm plugging in 50 for d, and I'm plugging in 9 for x. And then in the denominator, I'm also plugging in 9 for x. And I'm getting that this comes out to be approximately 21.42. The last part of this is asking us to graph this function. There's already a graph included for us. Notice that we can see a vertical asymptote in there at x is equal to negative 12. We can also see a horizontal asymptote in here at y is equal to 50 in this case, because in this particular example, d is equal to 50. And we knew that generally speaking, the horizontal asymptote would be at y is equal to d.